Fun fact about Adam, he probably doesn't sleep because it doesn't matter what time I submit the PR, 5 minutes later, there is a review on it. So, by him. So please, everybody, welcome Adam Hearn.
Hearn, yeah.
Who's going to be talking on redefining stream composition with algebraic effects.
So this talk will probably cover very little about stream composition, but it will talk about the innards of streams and what a stream is. So I hope you enjoy, and let's get started. So who am I? I'm a software engineer. I currently work at Amazon. You can find my GitHub. I like to contribute to projects. So if you have an interesting project, please tell me about it, and I'll read about it. I currently contribute to Kio, some to ZIO, some other small projects. But I'm very interested in functional programming, Scala. But it doesn't have to be Scala. It's just what I found to be the most fun, the easiest to write, all that stuff. So before we talk about algebraic effects or anything like this, we should talk about what is a stream. And I've watched actually a lot of talks on streaming because I was like, okay, I'm very out of my depth here. And a very simple definition I've seen, which it's basically, it's a collection of 0 to n elements. And I think this totally misses the point. This aims to simplify what is a stream, but it's very reductionist. And I think that's a problem. Because what really is a stream? It's a blueprint for producing 0 to n values. And I think the very, very important thing here is that it includes effects. So when you have a stream, you actually don't care about the iterator of values. And we'll talk about iterators in a moment. But you actually care about the I/O or the peer or the async or the abort or the fail, whatever you have in terms of effects, in terms of type classes, in terms of however your effects library encodes it, you care about what's being produced by the stream. You care about the remote requests being made for each element in the stream, whatever it may be. Of course, streams should be lazy, immutable, referentially transparent. I'm not going to talk about that. Let's move on. So, are streams necessary? I'm going to say no. We don't need streams, right? We have iterators. Iterators are built into the language, so we might as well use it. It's good, right? Like a lot of libraries support all that. They support infinite collections, so you don't need to instantiate every value in an iterator right into memory because they can lazily pull from some data source. But one problem is if you look at that signature, the next returning an A, we can immediately see that this is synchronous. This isn't Rust. There's no async function here in Scala. So this is a synchronous function. And that's highly problematic if you write performant async code, these sorts of things. The other problem is iterators are mutable. And I don't know about you, but this poses a lot of problems in terms of reuse, in terms of accidental capturing. So you have to be very careful when to use a def, when to use a val. These are things that I don't like. The other thing is they don't really support error handling. So you could throw in your next. Let's say we're building some infinite stream with an iterator. The only real thing you can do is throw. And I don't think that's a very good design. So we'll solve this. We'll build an effectful iterator. This is what I came up with. And I thought, OK, it's very simple, right? This will make it immutable. We can have some way of referentially transparently managing state, whatever we need to do. And so we'll try and implement this. So one beautiful thing that streams do give you is higher order functions, right? Being able to say map over an entire stream of an infinite collection allows you to transform your data without loading it all into memory. So we'll implement map. This seems pretty simple. Does anyone want to give me an answer on what next should be? OK, so it's outer.hasNext. Very simple. OK, I guess I lied on which function I was implementing. But then the next one is actually slightly more complicated, which is you have to get the element, and then you have to map over the I/O, and then transform the underlying element. OK, so clearly we can implement high-level iterators. We don't need streams. So let's keep going. Let's try implementing filter. All right, so the signature seems simple. We have two functions here, has next and next. And the real problem is that the function from A to Boolean is required to know if we have a next value. So we can try and implement this. But what happens to that element that we just checked for? It's gone. We had to have to manage the state some other way. And so the real problem is that hasNext is no longer statically known, and we have to manage the state of next using it becomes way too complex. So not only does this require advanced state management, it's not trivial to implement these high-level operators in something like an I/O iterator. So the other thing is this doesn't really have good support for resource management. Perhaps we could use like a io.ensuring, but it's like, where would you put that? There's all sorts of like problems with this design. And I'm going to tell you, this is probably a bad interface, and I designed it. So let's talk about some existing streaming libraries. I'm going to be focusing on the Scala ecosystem, but there's obviously many, many libraries. Most importantly, FS2. A lot of people like FS2. So what does the stream represent? It has an F of underscore, which is just some higher kind of type representing the effect type. So this could be I/O, this could be async, this could be whatever you want it to be. But you know, for example, this does support pure streams without actually any effects. The A is the return type, so the values you'll be transforming or operating across. ZIO is very similar, except there is no F, right? The effect type is always a ZIO. The R type is the values that are required to run the stream, and the E type are the potential failures. So this starts to be more useful to me because I like typed failures, but there's something missing, and we'll explore what that is. Kio is a bit different. It chooses to go with the result value on the left side, and that's reminiscent of the actual Kio effect type. We'll get to that later, but essentially the S here is simply the set of pending effects. So, how do streams work? Well, let's look at FS2. It's just a class, and it looks like there's some underlying value, which is a pull. And obviously, we can see that there's the F effect type. It's pushed into the pull. We can see the unit value on the far right side. That's different than the stream. This is simply the value that the pull completes with. A few things to note here. This is all covariant, so you can use a subtype effect and then mix in a supertype effect and all that. We'll get to that later, hopefully. So anyways, I don't really care about this pull thing. Let's just see how they implement map, because I think map is a very simple transformation across the stream. It should be trivial, right? Oh, well, unfortunately, everything is implemented in terms of pull. So this becomes very hard to deal with because we don't really know what a pull is. So I'm going to defer teaching you what a pull is, and we're just going to talk about ZIO, because that seems easier, okay? So what is a Z-stream? Oh, well, this is horrible. A Z-stream is actually just a channel, right? And it's a channel of R, any, E, chunk of A, any, and that seems even more horrible than a pull of F of A of unit, right? So, okay, that's fine, that's fine. We'll just go look at map. I assume it's going to be simple. Let's keep going. Okay, so it's a new Z-stream of channel.mapout.map.f. Okay, so clearly a stream is just an abstraction. That's all it is, right? In truth, there is no stream. The stream is what you are made to believe and is how you handle the data, but there really is no stream. So let's actually go explore what a pull and what a channel are, and then let's explore maybe why these aren't the best abstractions. So a pull is just an abstract class. All the variable type parameters are covariant. You'll note that it runs to an effect of F. So in this case, we actually don't know that what type that it runs to, but we'll get to that later. It emits values of A, which I guess emission meaning some sort of streaming operation, and it stops or completes with the value of R. So one way I like to look into this is generally there's a few simple functions us functional programmers like to use, flat map, map, these sorts of things. So let's start with flat map and let's unpack it. Okay, so I know there's a lot of code. I'm sorry, it's even smaller on my screen. But we can see a few things about the signature. First of all, they're instantiating a new class, and most notably, they're handling a few cases. So we'll ignore all the types, everything about that, but let's look at the function that's being implemented. So we have this continue thing, and in the case that it produces a successful value, we'll try to continue. And if that throws an error, we will fail. And if the result is interrupted, we'll actually just propagate that interruption straight through. And notably, if it's a fail, we'll do the same thing. Okay, seems pretty simple. Let's look at the next function from pull, pull.succeed. Okay, so now you guys are going to look at me and say, okay, we have flat map, we have pure, I guess this could be succeed, whatever you want to call it. What do we have when we have flat map and succeed? A monad, right? Yes, exactly. So we have this weird specialized monad with 3 type parameters. We don't really know what it does, and that's okay. Let's keep going. It's used for emitting values. That is one thing that we do know. And there is actually something very subtle about this, which is it's not fully here because there's some implemented methods. They're only implementing the one abstract method. But this actually has resource safety. This also supports aborting or failing the transaction or your whole stream. And it also supports interruption. So think very carefully, when we're manually encoding these things, where would those also appear? Well, the run loop, of course. So as we all know, when we write a monad, we then have to unpack it somehow. And if it's asynchronous or something that creates suspensions, we need something that is able to run this down to another value. In this case, we actually know what value it's going to produce. It's going to produce an f of b, which is some type class, some effect type, which supports some arbitrary number of operations. But notably, the type class required here is what? A monad error. So we know that we need some sort of effect that can fail, and I guess that's it. I don't know. But we'll keep going. A few things that are, I guess, interesting is obviously this produces an f of b. It discards the termination value, so maybe why do we even need that? Like, why does pull even care about this? Perhaps it's just a bad encoding. Maybe it's a good encoding. I wanted to show you the body of compile, because I think this is where the interesting things happen. But it turns out that it's 400 lines. And not only is it 400 lines, it's very complex Scala with very short names like Go. What does Go do? It's not very clear, right? But the very important thing we can see here is that we're encoding a run loop to fold the stream down to a single value. So in many cases, if you're running like a collect operation on the stream, this would be running it down to a single sequence of contiguous values. Okay, let's talk about Z-channel. Z-channel definitely provides more functionality than pull, but I could already tell like this is a little bit grotesque. I mean, we have like, what, 7 type parameters or something? So let's go through them. So Z-channel accepts both input and produces output. So this is slightly distinct. It requires an environment very similar to a ZIO. If you haven't used this, don't worry about it. We're not going to talk about it today. It accepts n elements of in element. So some arbitrary number of elements can be pushed to this Z-channel. It accepts only one in error. So as soon as you get one in error, the whole thing fails. It accepts one outdone, that should say indone, and it has some output. It produces 0 to n out elements. It fails with one out error, and it completes with one outdone. Okay, but what does it do? Essentially, this is for publishing and receiving bidirectional values. But that's okay. We don't need all that functionality. A Z-stream is simply, as I said earlier, an R of any, an E, chunk A, and any, which is simple, right? But more seriously, the Z-stream R is actually the Z-channel's environment. The in-air is unused. The in-element is unused. The in-done is unused. Well, at least mostly. And then the Z-stream E is actually just the output error. So a producer of values, or a Z-stream is producing values. So of course, it cannot accept anything, but it only can produce. So that's why we use the out channels here. And then of course, the Z-stream of A is the Z-channel out element. But notably, they're adding the chunk. And that's for performance reasons. When you have a stream, if you just suspended every element, it'd be very slow. So yeah, outdone is not meaningful here. Let's talk about flat map. So clearly complex signature like before. But in this case, there's a very interesting thing, which is it's going from outdone to another Z-channel. I'm not going to tell you why that's interesting. We're going to talk about that later. But the very important thing is, of course, ZIO encodes, instead of encoding the functionality in a method in an abstract class, this is encoded by using a distinct type fold, and then a majority of the functionality is encoded in the run loop. And so we'll talk about that as we go on. But first, this should say zchannel.succeed. And of course, this is very similar to our previous example of poll. What is a Z-channel? It's simply a specialized monad. So clearly, there must be a run loop, right? There must be a way to go from a Z-channel thing and produce some values or do something with this I/O. It's like the I/O in Haskell is useless if you don't run it, right? When I was a student, I tried to run Haskell and I didn't understand how to produce a value out of this thing. I wanted to get out of the box, but there was no way. And so that's what a Z-channel executor is. So this, the Z-channel executor, I guess it's just a channel executor, is essentially a stack-based executor, very similar to a fiber. And the very interesting thing about this is it's about 1,000 lines. Not only is it 1,000 lines, but it's 1,000 lines of very, very nested, complex code. So it's stack-based. It encodes interruption. It encodes providing environments. It encodes emitting values. So what do we have in common with the previous version of pull, right? Like we have interruption. I didn't include this here, but we have failure. We have providing environments. That's new. Emitting values, accepting values, right? So these things are somewhat mirrors of each other. Z-channel is obviously the superset, but much of the functionality is the same. And very interestingly, one thing that I would like to take a pause for, what also encodes these same things? A ZIO. So the whole point here is of a channel executor is to run a Z stream or a Z channel to a ZIO, right? But why are we double encoding a 1,000-line run loop between ZIO and a Z channel? This seems like mind-boggling, right? Like if you have complex, scary code, do you want to duplicate it and then hope that the parity of features are the same? Personally, I don't think so. But that's just me. So I added this function for fun because this is actually how you use a channel executor. And this is like, I don't know, 100 lines, 70 lines, whatever it is. But I really have no words for what to describe this is, except complex. And this is so much complexity that seems to just be introduced by having so much abstraction over producing values. OK, let's recap about what we've learned about FS2 and Z streams. First, let's talk about pull. So what is it really? It's a specialized monad. It has explicit resource scoping. I didn't talk about that very much earlier, but basically, at every layer, a pull has to check the scoping of resources it's using. And so this is very similar to like ZIO's scope, or Z-channel has a similar behavior. One thing that's notable about pull is it has implicit chunking. So all values are chunked always. So when you emit a value, it's used in a chunk. In Z-channel, that's not the case. What's interesting here is it mirrors a generalized I/O behavior. You encode success. You encode, I guess, some sort of side effect, which is producing a value. And then you encode interruption and failure. So this sounds very much like I/O, but clearly there's something different about I/O. Z-channel, on the other hand, it's also a specialized monad, which has bidirectional producer-consumer behaviors. It has explicit chunking. But notably here, it literally mirrors all of ZIO's behavior. So if you've ever gone into ZIO or any other functional effect system, and you've read through the fiber or the execution loop of these I/O monads, they're incredibly complex. They're complex for performance. They're complex for providing all these amazing, sweet features that feel baked in and a part of the monad. But the problem with that is that we're duplicating everything that we do because we have no way to abstract over these same things, right? Like if you think about it, a Z-channel or a pull could really just be a ZIO that had some other channel of producing value. So imagine if you had an I/O monad that just always emitted a log of all the values that you chose to emit. Well, actually, I don't say it here, but there's something called ZPure, and I don't know if you've used it, but it encodes a way to log values as you advance the computation. So conventional streams must encode all the capabilities of the effects they support. This is very, very important. Conventional streams are duplicating everything in effects, 100%, and that feels very wrong to me. So either we can only have streams or we can only have I/O, and maybe that's not true. So KEO. What is KEO? We're going to take a step back. We're going to stop talking about streams. Streams are terrible. So KEO is simply a generalized toolkit for Scala. It includes a functional effect system, and that functional effect system adds support for arbitrary algebraic effects. If you don't know what algebraic effects are, very simple. They're capabilities that are explicitly typed and explicitly need to be handled. It has first-class support for async and concurrency. In fact, I would argue that it's probably the fastest effect system on the JVM. It's mostly focused on performance, ease of use, and powerful features. So there's a lot you can do with Kio, but it's very simple. Each module is very well defined, very simple. Yeah, give it a shot. So let's talk about Kio's syntax, because it's very weird. I think this is probably the most strange syntax you'll see, but once you start using it, you'll be very addicted. So this is an effect, just like other effect systems, and it's, you might say, how do I read this, or what is this in code? This is a Kio effect returning a string pending I/O. So the I/O has yet to be handled, but eventually will produce a string. So there's this infix pending type. You get a result and effects. And notably, effects is actually, it could be anything, right? So it could be an int pending abort, which fails with some value, short circuits computation. But notably, you can actually put multiple effects in the pending set. So for example, if you have a file, it could be pending I/O and resource, and you might want to go handle one of those individually to scope the resource to some specific scope, but let the I/O bubble up. So let's talk about Kio effects. There's a bunch of them. I should have updated my talk because I wanted to include STM, software transactional memory, but I didn't. But I think that's one of the most interesting ones. There's I/O, obviously, suspends side effects. Environment pulls things out of the environment, contextually. This is very similar to ZIO's R-type. There's abort. So if you want to short circuit a computation and fail with an E value, you can do so. And notably, there's tracked errors and there's untracked errors. So those are panics. Like in Rust or other languages, you would say, OK, we need to panic. There's no way to recover from this operation. We'll fail the whole thing. Choice. This is another very interesting effect that is sort of unique to Kio. It enables exploratory branching over existing computations. So it turns your program, by default, Kio is supporting first-class multi-shot continuations. So you can do exploratory branching, prune certain branches. It's very, very powerful. But again, because these are algebraic effects, these are encoded in the Kio library, the effect handling is generalized. And so anyone can write an effect, and including user-defined effects. So one very, very important feature to Kio's behaviors as well as flow as a user is effect widening. And so a single value of any effect type can be type widened, which is actually a narrower type. But we're saying widened here because you're adding to the pending set. And so the interesting thing, of course, we're using a pure value here. But in general, if you have an I/O and it has some value inside, you can add a resource to that, and that doesn't change the underlying abstraction, but it requires you to handle it. And so this is very important for composition, because when you do a map or a flat map, you want to be able to put all your different effects in a for comprehension or using direct style, and not need to worry about manually transforming these values. So this allows for flexible compositional code. And interestingly, I think this is probably one of the only effect systems that does this, which is plain values can be widened to Kio computations. And this is an implicit behavior. So if you have a function that accepts a Kio computation, you can always just pass a value. And this is very useful for fluent code. Notably, widened values are not suspended, and widened values do not allocate. So I will note primitives on the JVM do, in a generic context, do allocate. But of course, if you pass a string, an object, whatever, you can get away allocation free, which is super, super powerful. So here's an example of using a bunch of different effects. And you can see that the signature reflects some of them, because I didn't put all of them. Resource is notably missing. So anyways, the important part here is that effects are merged by a map or flat map. And in Kio, they're able to be used interchangeably because of the way the type signatures work. It's very, very fluent. So that makes it very easy to teach people to code. And the resulting expression just combines all the effects. So in this case, it should be environment of string, async, abort. And you'll note we're using literal values to abort. I think this is the only effect system in Scala that supports literal values for basically anything. And then one thing that's missing, but it should be there, is the resource should be anded with the other effects. OK, so Kio Stream. What is it? Well, It's actually just a Keo effect. And that's the big secret about Keo and what makes Keo different, is there is no underlying representation which is different from an effect type. So you'll have no other monad. There is one monad, which is the Keo pending type. And the powerful thing of this is we're obviously using this emit thing, and you could see this explicit chunking. But stream is just a wrapper around a Keo effect. So this is mind-blowing because suddenly you can transform any value to a stream. And more notably, you can reason about how your computation behaves in the same way that you reason about your normal effects and how they change. So notably, this is an effect called emit. So let's take a brief look at emit. You'll note that it's currently unchunked, but I'm exploring some different changes of how we can chunk this or not. And really, you can think about this as very similar to Zpure's logging capability. So throughout the computation, you can log a value. It's pushed to the side. And then that value can be resumed later, and you can use it together. OK. You can emit multiple values. You can emit a single value, et cetera. So when you run this, I guess that's missing here, you produce a chunk of the values as well as the computation that the effect returns. So this mixes with all other Keo effects. So the beautiful thing is any value, any algebraic effect that you encode is automatically supported in your stream encoding. So here's an example. You could just basically emit single values as you go through your computation. And when we go to run this, you'll see we produce a tuple containing the values in the log from the emit, and then as well as the value produced by the computation. Does that make sense? OK. So let's look at stream's apply method. It simply takes a Keo computation, and it basically produces a stream. So the only thing that's sort of elided or hidden from the signature of the stream is, of course, the emit of chunk, because that's not necessary. The chunk already encodes the A in the second type parameter. So yeah, this just lifts any value to a stream. So let's look at Keo's map. And you're going to laugh, because this is obviously hiding all the complexity. But one thing I would like you to take a look at is, wait a second. This is map. This is not flat map. This is not map ZIO. This is not map IO. This is not map eval. This is map. So in Keo, because of the flattened encoding, we can essentially treat map and flat map as the same thing. But also, we can allow very fluent composition by allowing you to pass effectful or non-effectful computations or functions to your stream operators. This makes it super powerful to use, and I have an example later of how you can abort in the middle of a map. So you say, I've reached a value that's impossible, I should fail. OK, map chunk. This is where things get a little hairy, but I think what I want to talk about is not so much what is here, but actually what's not here. So briefly, we talked about how emit is simply an arrow effect. I didn't really get into details because it actually, frankly, doesn't matter. But the important thing is we have this handle loop, and it accepts the tag v. So the tag v is the emit of chunk of v. And I totally messed up the signature because I have a stream of A with a chunk of v, but that's OK. For the purpose of this demonstration, what I want you to think about is, what effects are we handling here? What do we see? We see, OK, we have an input. We have a continuation. We check if the input's empty, so an empty chunk. We just proceed with computation. If it's not empty, we apply the function. We check if it's empty. Then we continue with the computation. And then if it's non-empty, so we have a non-empty chunk, we proceed to emit it. And then we continue with the next continuation. So why am I trying to highlight this? This does seem like kind of some innards that are not very pretty. The important bit here is we haven't talked about the S. There is no other effects being handled. We are only handling emit. So the beautiful thing is all of your streaming operations, all of your stream behaviors are encoded in terms of emit. They're not encoded in terms of other algebraic effects. And so that's actually really the beautiful thing about Keo's encoding is individual effect handling is simply that. It's individual. So if you're running a ZIO, you have to handle all of the ZIO effects. You have to handle the R type, the E type, the A type. But in this case, we actually only care about the emit. So I promised I'd talk about arrow effect. I don't really want to, but I will. It basically accepts an arbitrary higher kind of type input, produces some arbitrary higher kind of type output. Essentially, it allows handling from f of a to f1 of b. And so this enables you to have many different encodings here. One example would be a sequence to another sequence. So there's all sorts of things we could talk about. If you want to talk about deep level, like nested effect handling, all these sorts of things, we should talk about it, just not on stage here. So arrow effect, notably, if we go back to the slide, this is using arrow effect.handle loop. So arrow effect provides functionality or generalized sort of handler methods so that you can handle individual effects or continuations. OK, so yeah, back to my previous point, which is where are the resource, the abort, the async? When we look at the FS2 encoding, we look at the Z-stream encoding, all of these have to think, OK, I have to re-encode all the behaviors of the monad that I already know about. I have to encode interruption. I have to encode resource safety. I have to include failing. All of these features are sort of doubly packed into the stream and the monad that they're supporting. So the beautiful thing about Kio is this is all in user code. So this is a very trivial example, of course, but let's assume we have a case class person. We have some arbitrary query, and we're going to produce some people using some async computation, which requires a resource. So I mean, think a DB connection or something. We can open it. We can close it. We'll go through a stream. So we'll say, OK, init the stream. We have some people's names. We map over it. We invoke the query. So notice we're not using map ZIO. We're just doing map. And this fluently encodes what is essentially querying to some remote database. And notably, this doesn't break chunking. So unlike ZIO, which for every element produces a new single value chunk, this doesn't break chunking. So I've been very careful. I added a bunch of tests to Kio so that we don't break chunking. So if you've ever had a performance sensitive piece of code, you broke chunking, you ruined everything for everyone, it was terrible, this won't do that to you. So then, of course, we want to filter based on age, and then we can just run it. And so obviously, what is a run stream? What does this do? This actually just gives you the underlying effect, which is producing, it's basically just a chunk, a person, and it's requiring some async and resource to be handled. OK, does this seem simple? Yes. OK, good. So let's talk about performance. I mean, let's be honest here. We have ZStream. We have FS2. We think these are good enough. We use them for everything. And the very important thing is we use them for videos. We use them for live streaming, all these sorts of things. If performance is bad, we suffer. And so it's OK if Kio modularizes your code or simplifies user implementation or helps abstract away different components. But we shouldn't care. Because we, as software engineers, do one thing, which is we serve the business that we work for, and we do our best, right? We try and make something as fast as possible. We try and make something as good as possible, serve the customer to the very high standard. And so this has actually been a very core part of Kio, which is every single function is optimized. I mean, not every, but a majority of the functions have benchmarks. So let's talk about the benchmarks. This is actually copied directly from the ZIO repository. So if you think this is an unfair benchmark, go talk to the ZIO people. But essentially, we're just taking some sequence, we're turning it to a stream, we're going to filter it, we're going to map it, we're going to compile it. In the case of FS2, that was the scary 400-line run loop that we talked about earlier. And now, fold it down, and this will produce some, I/O of chunk of integer, I guess. Or I guess actually it'll just be an I/O of integer. In the case of ZStream, things look very similar. ZStream from iterable, we filter it, we map it. In this case, there's no need to compile it or produce some I/O because the ZIO run loop is all encoded in this run sum function. So this produces a ZIO of any, nothing, and int. In the case of Kio, we do a very similar thing. It looks very similar. There is no run, there is no compile, yada, yada. Enough talking. Let's do the numbers. As of yesterday, this is the most recent mainline branch. You can see that fork cats and fork Kio look very similar, but synchronously, Kio essentially blows all the competition out of the water, which I'm very excited about. So this should be fun. This is representing the operations a second. So if we go back to one of these benchmarks, this is how many times this can be run per second on whatever machine this was tested on. If you're interested in the benchmark results or making better benchmarks, open a PR. I can send you a link to the JSON results, and so on. So let's recap Kio streams. Streams are just Kio effects. This is actually mind-blowing, and I think it may seem like very simple at first, but this totally simplifies both the complexity in terms of maintainability of the code base, but also as a user, when you say, hey, my zstream.interrupt on ensuring either monad error, whatever it horrible is, right? That behavior, when it doesn't match my expectations because I've used ZIO and I know what it's supposed to do, I've used cats, I know what these functions are supposed to do on the IO monad, but that doesn't match what I think it's supposed to do on the stream. Why are these things different? Well, Kio simplifies that because they're encoded in the same way. This supports any algebraic effect. So as long as it's encodable in Kio's effect system, then it can support it. So we could add exploratory branching to your stream. We could add environmental dependencies. We can add failing. We can add resource safety. And all of that is encoded separately from the stream. That is the beautiful part. There is no doubly encoding of all these features. It's obviously blazing fast. Like let's say even if it's just as good as the other competition, I think that's good enough, right? So that's my belief, anyways. There are some limitations, and we should talk about that. You'll note it's invariant in the produced values. So this is sort of a usability concern, right? So it can only be of type A. But I have some news, which is this is because emit of A is invariant. I've done some exploration like a few months ago in terms of converting emit to be covariant. But there were some limitations at the time with the tagging implementation. But that's where I get to tell you about my next fun announcement, which is the new version of Kio. So we've been working on this for a little while now. But there's a few historical limitations that Kio didn't support, which is nested effects. And so this was like a huge critique from a lot of people who hadn't used Kio. And they thought that must be very limiting and all that. It turns out it wasn't that limiting. But now Kio just added support for arbitrary nesting effects. So if you want to memoize and produce another Kio, you could do that. More importantly, there's an entirely new tag implementation, which enables allocation-free subtype checking. So if you use ZIO, if you use any tagging library, Azumi Reflect, these sorts of things, they introduce tons and tons of overhead in terms of, if you look at your profiler and you do any sort of operation which depends on subtype checking, you'll find all of these allocations because the runtime optimizations are very difficult in terms of the macro because you're allocating a new class at each tag instantiation. So Kio has a few optimizations to avoid that sort of per tag instantiation allocation, as well as optimize subtype checking. There's also a bunch of optimizations, fixes, and stuff. I'm going to publish this right after my talk. So if you want to try out Kio, I'd say go download this. The binaries are actually already in Maven Central. So huge shout out to Flavio Brazil. He's done a lot of work. The tag is brilliant. I think you should go look at the tag PR. But yeah, that's also where my next announcement comes in, which is Kio 1.0 RC. So we've been working very hard on Kio for a few years now. I've been contributing to Kio for about a year. And we're finally ready. We're finalizing all the APIs. We're finalizing the effects we ship with, as well as many of the features. We're hoping that everyone starts to provide feedback. There's been sort of a slow uptick of users. I've noticed more and more people reacting on the PRs and sort of providing issues and bugs. That's actually a great thing. If you find a bug in Kio, please, please, please submit an issue because really this is for you. There's a Discord, there's a GitHub. Check it out. So yeah, thank you. I just want to say thank you to a few more people, which is the Kio contributors, namely Flavio, creator of Kio. There's also John Hungerford, Kit Langton, a few others. They've all done some work on Kio, and it's been a lot of fun working with them. Also, thanks to the LambdaConf team for inviting me out here. It's been a lot of fun. So.
Does anybody have any questions?
OK. That makes it simpler.
Very difficult audience here. OK.
So this is coming from an outsider. I don't write Scala or anything on the JVM. But thinking about the kind of design space you articulated, are there downsides to the encoding you're using in Kio versus the others? I mean, you talked a little bit about limitations and whatnot, and you showed that you've done the work to get the performance the same. But it seems like, well, this is an obvious move. So it seems like, why hasn't someone done this before? And therefore, that leads me to ask, what are the trade-offs? What are the kind of engineering reasons why they might not have done this before? And where would you see it going from there?
There's probably like 5 or 6 things I could name. The first being, this is actually really only possible in terms of performance, in terms of simplicity, in terms of API design on Scala 3. So a lot of the features we're using features from Scala 3.6.3 or whatever as soon as that. So a lot of this stuff is bleeding edge. In general, algebraic effects are very, very new, and especially on the JVM. There's a few other competitors to Kio, but I say that loosely because I think they have different goals and different plans, right? Kio is supposed to be very generalized. Users will find effects, all sorts of sort of abstract definitions, which can be put together modularly. And I think there are some limitations, but namely, like this encoding is very novel, right? So one of the biggest issues we had for a while was you can only fork with certain effects. Like it only makes sense. Like if you require a resource, how do you fork with that? And so there were certain problems that we had to solve, which no one was talking about, right? Most of the algebraic effects are not monadic. I think this is the only monadic, maybe I won't say only. This is one of the only monadic algebraic effect encodings. This is also one of the first, I think, that has true first-class async, fiber, all these sorts of things. And there's some really cool stuff with how you handle computations as you join the computation, as you fork the computation. And so this stuff, I truly think Flavio has come up with some actually novel stuff. There probably should be a paper written on this. But in general, I think like when something's new, there are downsides which you cannot foresee. And I don't really know what they are. Maybe just because there's not a lot of code, your LLM can't prompt that well yet. But usually what I do is I just paste a few core functions from Kio, and then the LLMs pick it up in like a few prompts. So I guess there's a lot of future potential, and I'm very, very excited to see what there is. One thing I didn't mention is Kio is actually like 15 modules, like I don't know, something crazy. And that's intentional because you can adopt a specific portion of it. So one feature is the Kio scheduler. It's an adaptive scheduler which enables basically like as there's resources free in the system, more work will be done concurrently. And as the system starts to CPU throttle or other bottlenecks, it'll start to use less threads to make sure that it gets OS like priority in terms of actually scheduling some work. So Flavio has done a lot of work on that. There's like really allocation-free data types, truly more than I can talk about. So please check out the repo, github/getkio/kio. So.
If I may, Flavio does know things about the JVM that nobody else can tell.
Yeah.
Maybe that no one else in the world knows. He's actually a JVM contributor.
Yeah.
So this is a unique thing. This is someone who knows the JVM in and out, who's actually optimized megamorphic inlining.
Yes.
The hardest problem in the JVM, writing an effect system. It is truly unique.
That's it's incredibly impressive, and honestly, like a lot of people have asked me, like, okay, like, this was like a year ago. They're saying, well, this is like a sort of a small project. It's not used in production yet. Like, whatever. Why would you even work on it? Like that sort of thing. And I had to tell them, I'm like, there's something very addicting when you've realized you're touching novel code, which has not been seen before, which has not been written before, which is basically impossible to describe in other languages and other libraries. And so when you have something so new, I think it's definitely worth trying. And if you can, the other cool thing is like there's integrations with ZIO, there's integrations with cats. So if you want to turn your ZIO program into a cats program, if you want to turn your ZIO or cats program into a Kio program, you could do that. So yeah, give it a shot. Let me know what you think. If we have any more questions.
We have 5 more minutes, so are there any more questions? No.
Yeah, could you briefly touch on like how like Kio streams like approaches back pressure and like stream termination, like as someone coming from Z streams?
So yes, very similarly. So the effects, one thing that I think is like very hard about naming things is, I guess we talk about this maybe somewhere. where is it, emit. We talk about this thing emit as if it's producing values. But one thing about continuations is this continuation has to be evaluated to actually produce values. So it's sort of straddling the line between a push and a pull implementation. So very similar to like a Z-stream. If you have an async, you have a fiber running, and it's going to produce a value eventually, the producer has to wait on that. So since it's pull-based, I mean, I would call this pull-based. You might disagree with me, and if you do, we should come talk in the foyer or whatever. But the interesting thing is, if you have to wait for the next computation, the back pressure is already there, right? The consumer is having to wait for it. ZIO or Kio also has like very performant channels, or like similar to like ZIO's queue, and they're very lightweight. And so we have added operations like buffer. So if you want to do something like, buffer in sort of a time period, or buffer some number of elements so that your producer can wait, and you can do that. So I'd say it's very similar to Z-streams. Honestly, I haven't spent enough time in the Z-stream code base. And if we go back to the channel type, I think it's reasonable for me to say no one has spent enough time in this code. So it's like this is a little bit insane. And so yeah, I would have to look more into how ZIO does stream back pressure. But essentially, it's a pull-based-ish. So yeah. You have a question?
I have a question, yeah. Sorry, I'm going to move away from the mic. So from my experience, nobody wants to work with streams unless they have to work with streams, right?
Yes.
And some of the use cases that you want to work with streams is files, but not really. But the main ones are like HTTP requests and Kafka and things like that, right? Does Kio currently provide integrations with those? If not, is that planned to be provided out of the box, or are you planning on the community stepping up and creating those integrations?
Yeah, so we have a HTTP client, and I think in terms of Kafka, there was some. Honestly, I don't deal with those libraries, so I don't follow it very closely. But Cal, he's a ZIO contributor. He had worked on Kio Virgil, which is I think integrated with Kafka, but it could be another Java library. I was slightly horrified when I looked at the internals, not because of his work, but because of the Java library and how they integrate with types and all that. But the short answer is it's a mono repo. There's a bunch of repos. We're willing to add anything that people use. So if you're like, oh, I want to work with Kafka, I want to work with whatever, we'll not only build it, but also because it's a mono repo, we found that it's like when there's transformations of the library, everything gets updated at once. Like one of my pet peeves with the ZIO ecosystem is that a new version of ZIO is published, and it takes exactly 10 years for the library authors to catch up and publish their versions. And I get it, like Chris talked about this morning, open source is this common good, and currently it's anarchy, and I'm going to butcher what he said, but essentially, because this is distributed, it makes the problem much harder to keep up with. So yes, the things you want to deal with streams we're working on. So.
And I think
we can make it quick.
One, let me just bring you the microphone.
A brief question is, if I wanted to run a server and have a time window based like dynamic batch, like collect a bunch of requests within this time period and blast them back at you, just for like micro batching,
Okay.
would this be something I could quickly build with that?
I mean, I think so. What I would do is I'd probably have some loop which pulls for values, and that could be emitting values using emit. You could turn that into a stream, and then you could push those values to a channel, or however you want to do it. You could use grouped within some time sequence, whatever the operators are, and then you could do some sort of draining and returning to the response. But yeah, I mean, streams are not the perfect abstraction for everything, as witnessed by me not using them for everything. But there's a lot of ways that you can use streams. So yeah.
Thank you.
By the way, I was just being told that there is a break followed up, so if we want to have more questions, we have time for more questions. Any other questions?
Great.
Well, I guess that makes things easier. Well, thank you very much, Adam. That was a wonderful talk.
Thanks.